Good day everyone, this is Engineer Bugarin and I will be discussing the principles behind each important topics of our subject course CE 521 Foundation Engineering. But before you proceed to the video, I recommend to review your soil mechanics, especially about the basic properties of soil, so as to for you to easily understand or follow the topics being discussed here. All right. So the first topic we will be focusing on is the subsurface stresses in soil. We have what we call the geostatic stress. So when we say geostatic stress, this is the stress due to the self-weight of the soil layers. In order to solve this stress, it is very important to identify first the properties of the soil that contributes to the geostatic stress, and such properties as the specific gravity, the void ratio, the porosity, and most importantly, the unit weight of the soil. Let's say we are interested in solving the stress at point A, located at a certain depth Z from the ground surface. For the sake of our calculation, let's assume that the unit weight of the soil is given as gamma. And so to calculate the total stress at point A, you just have to take the product between the unit weight of the soil and the depth Z of point A. That means the total stress at point A is equals to gamma and Z. It is also the same way of calculation when there is more than one layer of soil above a point of interest. Let's say this one. Assuming that each layer has thickness Z1, Z2, and Z3 and their corresponding unit weight of gamma 1, gamma 2, and gamma 3, the total stress the soil grain experience at point A is the sum of all the stresses for each layer above the point. That means the total stress A is equals to the product between the unit weight and the thickness of the soil at layer 1, layer 2, and layer 3. So now let's magnify our view at a certain region around point A. So you can see that there are the soil solids and the void spaces are filled with water. Suppose we would like to cut a section within this region and analyze what are the actual stresses acting upon this section. So as you can see, there are soil solid or soil particles that is being attracted to one another, and that force of attraction at the point of contact contributes to what we call the effective stress, or we just denote or designate effective stress as sigma prime. Effective stress is the portion of the total stress carried by the soil particles. It is also known as the intergranular stress. Alright, so now, but since the point of contact between each particle, solid particles, is so small that it looks that it will not cover the entire section. So there are area within this section that looks empty, right? But it is not actually empty. Remember that our assumption that the void spaces are filled with water. So there are water particles acting on the specified section, and these forces contributes to what we call the neutral stress, and we designate neutral stress as U. And neutral stress is the stress carried by the water particles or the water within the void spaces, or what we call the pore water. It is also known as the pore water pressure. Summing all these stresses acting upon the section gives us the what we call the total stress, sigma. So total stress is the sum of all the stresses, including the pore water pressure, the intergranular stress, and or the applied external stresses. So that means by expression, total stress is equal to the effective stress plus the neutral stress. But since we are more interested in solving the effective stress because it is one of the parameters that is used to measure the strength of the soil, let's just rearrange the terms so that we can have an equation that gives us the value of the effective stress. So sigma prime is equals to sigma minus U. But remember when I discussed the geostatic stress, to calculate the total stress, you just have to take the product between the unit weight of the specific soil and its thickness. So that is gamma z minus the pore water pressure, or the neutral stress can also be calculated by the product of the unit weight, this time of water, and the height of the water column above the certain point of interest. But there is a special case where the soil is submerged. So when we say submerged, the soil is below the groundwater table. So in this case, sigma prime, or the effective stress, is equal to gamma sat. So we have here the bulk unit weight. We change it to gamma sat because the soil is now submerged. So we can safely assume that the unit weight, or that the soil is fully saturated. Multiply by Z, or the depth or the thickness of the soil below the groundwater table, minus gamma of water times Z. Now if you can see that there is Z in both terms, we can factor it out of the equation. So we can have gamma sat minus the gamma water multiply by the thickness of that specific soil submerged in the groundwater table. So if you remember from your soil mechanics, there is an equivalent variable or term for the difference between gamma sat, or saturated unit weight, and the unit weight of water. And yes, that is what we called gamma prime, which is known as the effective unit weight, or the submerged unit weight, and can also be calculated using the formula GS minus 1 all over 1 plus E times gamma of water. Alright, so that's it for the discussion between these types of stresses. So I think it is better if we start solving problem. So let's solve problem number 1. Problem number 1 is, given the soil profile as shown in the figure, plot the total, neutral, and effective stresses with depth for the entire soil profile. And B, plot the total, neutral, and effective stresses with depth if the groundwater table rises to the ground surface. But hindi mo natin pansinin yung part B. Let's focus on part A muna. Plot the total, neutral, and effective stress para sa ating soil profile given. So we have on the top layer the sand. We have also given the property para sa density of the soil solid, which is 2.7 megagrams per cubic meter, and the porosity of 0.50 or 50%, while the clay, which is beneath the sand layer, we have the saturated density, which is equivalent to 2.00 megagrams per cubic meter. But remember na bago tayo makapag-solve ng mga stresses, we need to solve first the unit weight of each layer of the soil. So let's start with the sand layer. So wala pa namang binigay na unit weight dito, so pwede pa nating gamitin tong mga properties na to para ma-solve yung unit weight. So we have here the density of the soil solid, which is equivalent to 2.7. And remember sa soil mechanics that the specific gravity of soil solids is the ratio between the density of the soil solid and the density of the water. So we just have to plug in the value of the density of the soil solid and convert it to kilograms, since naka megagrams pa naman yung given. So we have 2.7 and then convert lang natin to kilogram, so that ang gagamitin natin unit weight of water, or the density of water, is 1,000 kilogram per cubic meter. So ang matitirang unit na lang natin dito is actually wala na, since specific gravity of the soil solid is unitless. So, ang value ng GS natin is 2.70 para sa sand. Regardless kung nasa above the groundwater or below the groundwater table yan, as long as it is sand, so the GS or the specific gravity of the soil solid is 2.7. Now, we have also the value given for porosity, which is 0.5. But you can use void ratio. Pwede mo naman i-convert yung porosity to void ratio para mas madali na ilagay sa formula na familiar tayo regarding the unit weight of the soil. So, the formula for the void ratio given the porosity is N over 1 minus N. And N, lagay lang natin yung value na given, which is 0.5, and we will have a value of 1.00 para sa void ratio ng sand. Now, kung pag-uusapan natin muna yung sand layer above the groundwater table, since wala namang binigay na condition na merong saturation above the groundwater table, you can always assume that the sand or the soil above the groundwater table is always dry. Unless otherwise saturation is given. Pero sa part na to, sa problem number 1, wala namang binigay, so we can assume that the sand layer above the water table is dry. So if it is dry, pwede mo nang gamitin yung formula ng dry unit weight, which is equivalent to GS gamma water all over 1 plus E. Now that we have the value for GS and the void ratio, and gamitin natin na unit weight of water is 9.81, pwede mo nang isolve yung value ng dry unit weight. And the value of the dry unit weight is 13.24 or 244 kilonewton per cubic meter. This is only applicable sa dry part ng sand, which is above the groundwater table. Iba kasi yung mangyayari below the groundwater table. Dahil ito ay below the groundwater table, the sand layer is submerged and therefore it is fully saturated. So, we have to consider the sand layer below the water table, submerged and saturated. So, pwede kong gamitin yung formula for the saturated unit weight of the soil given by this expression GS plus E all over 1 plus E multiplied by the unit weight of water. Kompleto na rin yung mga values na yan. I-input lang natin yung GS, yung E, and yung gamma water. And then we will have the value for the saturated unit weight of the sand below the groundwater table. That is 18.149 kilonewton per cubic meter. Applicable lang yan doon sa sand below the groundwater table. So now, meron pa tayong clay layer, which is obviously, kung mapapansin nyo, submerged din yan and fully saturated, kaya pwede kong gamitin na lang. Pero dahil given na rin naman yung density, yung saturated density ng clay, i-multiply mo na lang yan by the gravitational acceleration. So, gamma sat is equal to this value. So, convert ko lang yung ating saturated density na 2 megagrams per cubic meter to kilogram per cubic meter. Ayan, kinonvert ko lang. Minultiply ko siya by the gravitational acceleration 9.81 meter per square second, giving us the unit. Alam naman natin ang product between kilogram and meter per square second ay Newton. Kinonvert ko lang yan to kilonewton by dividing it by 1,000. So therefore, ang ating saturated unit weight para sa clay layer below the water table, which is submerged and saturated, that is 19.620 kilonewton per cubic meter. So, yan yung gagamitin natin para sa pag-compute ng stresses, total, neutral, and effective stresses. So, let's start. Siyempre, total stress muna tayo. Summation lang to ng mga stresses above a certain point. So, let's start with point 1. So, sabihin natin na this is point 1. This is point 2 dito sa interface o sa groundwater table natin, and point 3 yung interface between sand and clay, and point A yan, but let's say this is point 4 just below the clay layer. So at point 1, so at at the ground surface, since ang formula natin is gamma z at ang reference ng z natin ay from the ground surface, so therefore the value of the stress at the ground surface is 0. That is 13.244 para sa sand, multiply by 0 kasi yung z natin ay measured from the groundwater table, ground surface, so this is 0. Kaya meron tayong total stress of 0. Next, at point 2, doon sa ating mismong groundwater table, pero ang pag-usapan natin lang ay a little bit above the groundwater table, na kung saan dry pa rin yung ating soil, so ang gagamitin pa rin nating unit weight ay 13.244, pero kailangan mong i-sum up yung mga nakuha mo sa taas. So, ang nakuha natin above the sand layer is 0, so isama mo na yan, although 0 naman yan, pwede mo namang i-neglect, plus the stress due to this layer. So, yung stress due to this layer is 13.244 times 2 meters. So, ayan. So, idadagdag mo lang siya dun sa 0. Kaya, ang magiging total stress natin at this point is 26.488. So, ilagay lang natin siya dun sa ating diagram. So, meron na tayong 26.488. So, ito ay linearly varying dahil yung property naman from this point up to this point is consistent or same lang naman. Hindi naman nagbabago yung property ng sand from this point up to this point. So now let's continue. Let's solve the stress at point 3. So let's consider this as point 3, the interface between the sand and the clay layer. So to calculate the stress, the total stress, first kunin mo muna to. So that means 26.488 dahil ang 26.488 is the total stress from this point upward. So yan na yung summation ng stresses above. So para makuha mo yung stress dito sa interface between the sand and the clay layer, idadagdag mo na lang yung stress due to this layer. So we have 18.149 times 2. Idadagdag mo na lang siya doon sa 26.488 so that the total stress at this point is 62.786. So, lagay lang natin. So, ito, iba na yung slope ng line. Kung i-compare mo siya dito sa slope ng line kanina, bakit magkaiba sila? Parehas lang naman silang sand. Ito kasing nasa taas ay dry, at yung nasa baba naman na sand ay saturated. Kaya magkaiba sila ng property, magkaiba sila dito ng slope. And lastly, we have, para sa last layer natin, para makuha natin yung total stress at this point, at the bottom, that means kunin mo muna yung total stress na above this point, that is 62.786, and then idagdag mo na lang yung stress due to the clay layer. So that means the total stress is 62.786 plus the stress due to the clay layer, that is 19.62. The unit weight of clay times the thickness of the clay is 4 meters, giving us the total stress of 141.266 kilopascal. So, yan ay iba rin ang slope niyan. Siyempre, kitang-kita na rin naman na iba naman kasi itong property dito. Dahil ito ay clay at ito ay sand, so magkaiba rin to ng slope. So, ayan. So, meron na tayong graph para sa total stress natin. So, now, let's proceed sa neutral stress. So, sa neutral stress, ang pinag-uusapan na lang natin dito ay tubig. So, tanggalin mo yung mga lupa and then i-analyze mo na lang yung tubig. Siyempre yung water na yan is naka-reference tayo dito sa groundwater table. So ibig sabihin, below the groundwater table ay punong-puno ng water, yung mga void spaces natin kasi nga we assume that below the groundwater table yan ay fully saturated and submerged. So let's proceed now sa ating neutral stress. So, kung mapasin nyo sa point 1, dahil wala namang tubig dito dahil we consider it dry, so 0 na yung mga stresses dito. Neutral stress ang pinag-usapan, kaya 0 yan, 2. Kasi dry yung nasa taas ng groundwater table. Pero once na mag-proceed na tayo doon sa third point, dito sa ating next layer, sa interface between the sand and clay layer, meron ng tubig. Tama ba? Kasi dito nag-umpisa dito nag-umpisa sa groundwater table. So habang bumababa ka, nakaka-experience ka ng pressure due to the water particles. So yung pressure natin at this point is the unit weight of water. I-add muna natin pala to 0 and then plus the unit weight of water times the height of water at this point. So at this point, the height of water is 2 meters that is measured from the groundwater table. Kaya ang total neutral stress is 19.62. Lagay lang natin. Ayan. And next, punta tayo sa point A or at the bottom of the soil profile. So, mapansin natin, at this point, dalawa yung way na pwede mong gamitin to calculate the pore water pressure. Parehas lang naman. Pwedeng ang gawin mo is 19.62 tapos mag-plus ka na lang ng stress ng water para sa 4 meters na to. So, that means meron kang 19.62 plus 9.81 na unit weight of water times the height of water para sa clay. Or, dahil tubig lang naman yan at iisa lang naman ang property, pwede mo rin gawin na yung 19.62, ito yan, or times 4. Ito yung ginawa natin kanina. Or pwede mong gawin din to. Parehas lang yan ang kalalabasan kung ang gagawin mo is 9.81. That is the unit weight of water times 6. Kasi kung gusto mo lang malaman yung pore water pressure at this point sa ilalim, edi pwede mo namang i-total na lang to as 4 plus 2, which is the height of water at point A, will give you the same value, 58.86. So, ayan. So, same slope lang ang gagamitin nating line dahil property lang naman to ng water at pare-parehas naman ang property natin ng water kahit saan siya mapunta, kahit sa sand or sa clay, it is still water of the same property. Okay, so ibalik ko lang yung nakuha nating total stress and yung ating kakatapos lang ma-solve na neutral stress. Kasi gagawin na natin ang effective stress. So, sa pagkuha ng effective stress, ang sabi ko sa inyo kanina, difference lang yan ng total stress and the neutral stress. So, kunin mo lang yung difference. 0 minus 0 is 0, obviously. Ayan, so meron tayong 0. 26.488 minus 0 para sa ating effective stress, yan ay equivalent sa 26.488. And then, at this level, meron kang 62.786 minus 19.62. Ang ibibigay naman sa atin ay 43.166. And lastly, at the bottom of the soil, we have the difference between 141.266 and 58.86 will give us value of 82.406. And this is the pressure diagram when the groundwater table is located 2 meters below the groundwater table. Dahil sa part B, ang gagawin natin, yung groundwater table ay aangat at magko-coincide doon sa ground surface. Ano kayang mangyayari? Ano kayang effect nito sa ating effective stress? So, let's proceed to problem number 1, part B. Plot the total neutral and effective stress of the same soil layers with depth. Kaso nga lang, ang groundwater table na natin dito rises to the ground surface. So that means yung kaninang layer na dry above the groundwater table, this time, fully saturated and submerged na rin. Kaya ang ginamit ko na lang, kinuha ko na lang yung computation natin kanina na saturated unit weight ng sand. Since wala namang dry part dito sa sand. Alright, so, proceed na agad tayo sa total stress. So, ganun ba rin, kunin natin yung total stress at different points ng ating soil profile. Sa taas, sa ground surface, the stress is 0. Gamma times 0 is 0. And then, proceed tayo sa susunod na level, the interface between the sand and the clay, that is 18.149 times the height of the sand layer. So, ibig sabihin, ito yung total stress na na-experience ng mga particles natin dito sa level na to. 18.149 times 4, and that is equivalent to 72.596. Now, let's proceed sa baba, sa pinakailalim ng ating soil profile. So, para makuha mo yung total stress dito, that means, kopyahin mo to, yung 72.596, dahil yan na yung stress due to sand, idagdag mo na lang yung stress due to the clay layer. So, that is 72.596 plus the stress due to clay, that is the unit weight of clay, 19.62 times 4, giving us a total stress of 151.076 at the bottom of the clay layer. So now, ang magbabago, syempre, yung ating pore water pressure, dahil umangat yung groundwater table natin, iba na yung mga value natin dito for the pore water pressure. So, umpisahan natin sa taas. Obviously, this is still 0 pa rin naman. The pore water pressure is 0. And then, proceed tayo dito sa second level, na kung saan yung height ng tubig natin at this point, from this point ay 2 meters papunta sa ground, 4 meters papunta sa groundwater table. Kaya meron kang 9.81 the unit weight of water times the height of water, which is 4 meters at this point. So, meron tayong value of 39.24. And last, pwede mo namang gamitin dito sa ilalim, sa clay naman natin. Pwedeng ang gawin mo is 9.81 times the total height from this point up to the groundwater table. That is 8 meters. Parehas lang yun. Kung idadagdag mo yung 39.24 sa pore water pressure ng clay layer lang, parehas lang yun. So, ang gawin natin, sige, pwede naman, 39.24, copy mo. And then, idagdag mo na lang yung pore water pressure para sa clay layer. That is 9.81 times the 4 meters para sa clay layer. Same lang din yung ibibigay na value kung ang gagawin mo ay 9.81 times 8. O yung total height ng water natin at this point. So, ibibigay pa rin yan yung 78.48 na value. Same slope to. Dahil parehas lang naman ang property ng water natin all throughout the soil profile. So, kompleto na yung ating total stress and pore water pressure. Kunin na natin yung difference para sa effective stress. So, 0 minus 0 is 0. 72.596 minus 39.24 will give us a value of 33.356. And then, at the bottom of the soil, we have 151 minus 78.48 will give us 72.596. So, just a recall, naalala pa na para ma-solve natin itong 72.596, ginamit lang natin yung formula na gamma Z. Tama ba? So, this is gamma sat, pero this time yung gamma natin ay saturated dahil ito ay below the groundwater table. It is submerged and saturated. And para naman sa water, we have syempre gamma ng water times the height Z, which is parehas lang din naman ng ginamit nating height dito. Kaya yung 33.356 is just the difference between the total stress and the pore water pressure. So, ilagay natin yung formula. Ito yung ginawa natin kanina. And then, gamma prime is sigma prime is equals to gamma prime times Z. Where gamma prime is, sabi ko nga sa inyo, the submerged unit weight or the effective unit weight given by this formula or the expression GS minus 1 over 1 plus E times the gamma of water. But, remember, kung gusto mong gamitin tong formula na to, nare-rekta ka na sa gamma prime, walang problema yan. Kaso lagi mong tatandaan, allowed lang tayong gumamit ng gamma prime kung ang soil natin ay submerged. Submerged lang dapat. Kaya dito, pwede mo nang makuha directly yung stress at any point kung submerged yan. So, kunin mo yung gamma prime para sa sand. Kunin mo yung gamma prime para sa clay gamit yung formula na to. And then, i-multiply mo siya by their corresponding thickness. Ito na agad ang ibibigay sa iyo kahit hindi ka na dumaan ng total stress and neutral stress. But remember, naggagamitin mo lang ang gamma prime na yan if the soil is submerged. Alright. Okay, so now, let's proceed to another topic. Tapos na tayo sa problem number 1. So, let's talk about the effects of capillary rise in the soil stresses. Ano nga kaya ang epekto ng capillary rise? Patataasin niya kaya yung effective stress or pabababain? So, malaman natin yan kapag nakapag-solve tayo ng problems regarding the capillary rise. Pero ano nga ba yung capillary rise? So, if you remember from your fluid mechanics, capillary rise is associated by this the tensile forces, tama ba? Na naderive yung formula because of summation of the tensile forces on the surface of the water. So, kapag naglagay ka ng tube with a small diameter sa surface ng tubig, the tendency of the water is magra-rise up to a certain height. Tama? So, ganun din yung gagawin natin. So, i-relate lang natin yung capillary rise in tube sa capillary rise sa soil. Dahil meron tayong mga void spaces. Tama ba? Meron tayong mga void spaces. Kaya pa natin siyang i-consider as continuous tube na kung saan doon pwedeng mag-rise yung tubig. So, capillary rise, this is the phenomenon in which the water rises above the groundwater table against the pull of gravity but is in contact with the groundwater table as its source. So, aangat. So, yung tubig pala ay manggagaling sa groundwater table at aangat because of the void spaces, doon siya papasok. Doon papasok yung tubig. Aangat at a certain height, which is what we call the height of the capillary rise na kailangan nating computein dahil nakakaapekto ang capillary rise sa effective stress ng soil. Tingnan natin kung maganda nga ba ang ibinibigay na effect ng capillary rise sa soil or hindi. So, let's solve problems regarding the effects of capillary rise in soil stresses. So, ang gagawin lang natin dito ay same pa rin ang ginagawa natin kanina sa pagkuha ng total, neutral, and effective stress. Medyo magbabago lang dun sa part na merong capillary rise. Okay, so problem number 2. A layer of silty soil of thickness 5 meters lies below the ground surface at a particular site, and below the silt layer lies a clay stratum. So, meron na naman tayong 2 layers of soil. We have the silt and we have the clay stratum below. The groundwater table is at a depth of 4 meters below the ground surface. Plot the stress diagram and determine the effective stress at points A, B, C, D, and E. So, ito yung given na soil profile. So, ito yung groundwater table. Madali mo nang ma-identify na groundwater table yan kapag merong triangle. Ibig sabihin ito yung surface ng groundwater table. So, given yung properties ng silt, we have D sub 10 or the effective size, the void ratio, specific gravity of solids, and C. Dito mo agad ma-identify na merong capillary rise dahil binigay yung tinatawag na capillary constant C, 0.504 square centimeter. And dito naman, meron tayong clay na given din yung void ratio and specific gravity of the soil solids. So, kung titingnan natin, ito yung groundwater table, nasa part siya ng silt. Na kung saan kapag nagkaroon ng capillary rise, the tendency of the water from the groundwater table will rise up to a certain height. Yun nga lang, hindi pa tayo sure kung hanggang saan yung aabutin ng capillary rise. Pwede na tayong mag-compute ng height ng capillary rise gamit yung formula na to. So, H sub C is the height of the capillary. Capillary rise is equals to the capillary constant C divided by the product of the void ratio and the effective size. So, i-convert na lang natin yung mga unit kasi may mga millimeters and centimeter. Convert nyo na lang to meter since ang mga dimension naman natin dito sa soil profile ay naka-meter. So, by just plugging in these values sa ating formula and converting them, gaya ng C natin, from square centimeter, ginawa kong square meter, and from millimeters sa ating effective size, convert ko na lang to meters, giving us the solution to this equation equal to 4 meters. So, the height of the capillary rise para dito sa ating problem number 2 ay 4 meters. Yang 4 meters na yan, lagi yung measured from the water table kasi yun yung source ng capillary rise. So yung tubig natin from the groundwater table ay aangat daw ng 4 meters. Eksakto 4 meters yung hanggang ground surface. Kaya yung tubig from the groundwater table ay magko-coincide hanggang doon sa ground surface. So that means yung silt kanina, kung sakaling walang capillary rise, dry dapat siya. Kasi above the groundwater table, we consider it dry. Pero dahil nagkaroon ng capillary rise, naging saturated siya, fully saturated, unless otherwise na in-specify sa problem na meron siyang certain degree of saturation. Pero dahil wala namang binigay na degree of saturation dito sa tinatawag nating capillary zone or capillary fringe, consider mo na lang siya na fully saturated. So, gawin natin. So, dahil fully saturated na yung silt layer above the groundwater table, ayan, fully saturated, and the same na rin naman siyang, since saturated na rin naman tong ilalim, obviously kasi submerged siya by the groundwater table, so isa na lang yung computation para sa saturated unit weight above and below the groundwater table para sa silt, kasi parehas naman silang saturated. So, yung same formula pa rin tayo. And then, input lang natin yung mga values given. We have the specific gravity of solids and the void ratio and the unit weight of water as 9.81 kilonewton per cubic meter. So, solving this equation, the saturated unit weight is equivalent to 19.62 kilonewton per cubic meter. Para na yan sa buong silt layer. Regardless kung above the groundwater table or below the groundwater table, basta nasa silt area tayo or silt region, yan yung gagamitin nating unit weight ng soil. And next, for the clay layer, so ayan, so dahil ito ay below the water table, it is submerged and saturated. So kung saturated yan, edi gamitin pa rin natin yung formula na to. Alright. So, pwede ka nang gumamit actually ng gamma prime kung gusto mo na ng direct computation. Kaso nga lang, kaya hindi ko pa pinapagamit yung shortcut na gamma prime kasi pagdating sa capillary rise, maaaring magkamali ka. Dahil baka makonsider mo na itong nasa capillary zone ay submerged. Hindi ganun. Lahat lang ng submerged ay yung below the groundwater table. Although ito ay saturated, that doesn't mean na siya ay submerged. Alright? So, saturated lang siya, hindi siya submerged. Pero yung mga soil below the groundwater table is always submerged and fully saturated. Okay, so ang gamma sat para sa clay layer natin is 19.348. So, yan yung gagamitin natin later on sa pag-solve ng mga stresses at points A, B, C, D, and E. So, mag-umpisa na tayo sa total stress. So, 0 pa rin yan. Kung isosolve natin yung stress at point A, that is 0, gamma, the unit weight of the silt times the height with respect to the ground surface ay 0. Kaya 0 na yan. Proceed tayo sa point B. So, sa point B, meron tayong unit weight ng soil, 19.62 times the height from the ground surface to the point B, kasi doon tayo kumukuha ng stress. So, that means 2 meters lang yan. Kaya 19.62 times 2 will give us a value of 39.24. Baba tayo at point C. Kunin natin yung stress. So, dalawa yung computation dahil pare-parehas naman tong silt at saturated. Pwedeng ang gawin mo na lang ay yung unit weight na to times mo sa height mula sa groundwater table hanggang sa point C. Okay lang din yon kung ang gagawin mo naman ay yung 39.24 para sa stress sa point B, i-add mo na lang yung stress dito na ilang meters to. 4 to 2, so 2 meters din to. So, pwede yon yung 39.24 times 9 plus 19.62 times 2. Or, 19.62 times the total height from point C hanggang sa ground surface. So, yun na lang yung gawin natin. Mas mabilis lang yung computation, giving us the value of 78.48. So, next, sa point C. So, silt pa rin naman ito at saturated. So, dapat yung slope ng line natin pare-parehas tulad nito kasi parehas lang ng property yan. Kaya sa point D na pala tayo. Sa point D, pwedeng gamitin mo 19.62 tapos yung total height from point D to point A para makuha yung total stress, or pwedeng ang gawin mo na lang yung 78.48 plusan mo na lang ng stress para sa layer na to. Parehas lang yun ang ibibigay at ang stress at point D is 98.10. So, kung mapapansin nyo, same slope to mula dito sa taas hanggang dito dahil pare-parehas naman yung silt and parehas din siyang saturated. And last, we have the clay layer. So, sa clay layer, ito yung ating unit weight. I-multiply na lang natin siya by 1 since ito yung thickness ng clay layer. Tapos, i-add natin siya doon sa total stress sa point D para makuha yung total stress at point E. That is 98.10 plus the stress due to the clay layer. Ito yon, product ng unit weight and the thickness will give us a total value of 117.448. Iba na yung slope nito dahil clay layer to, hindi naman to parehas ng property dito sa silt. So, proceed tayo sa tubig. Ito, dito na nakaka-apekto talaga yung capillary rise sa pore water pressure. So, last problem, nung nag-solve tayo ng stress doon sa tuktok, sa ground surface, tama dahil dry yun, kaya 0 yung naging stress natin sa tuktok. Pero ngayon dahil ito ay naging saturated because of the capillary zone, we expect na meron na itong value. At ano kaya yung value? Kung mapapansin ninyo, para sa sign convention natin, so itong mga value na nakuha natin sa total stress, kanina rin sa pore water pressure, lahat yan ay compression. Tama ba? Na itong 39.24 sa point B is the stress due to the weight. So ito yung na-experience ng point B na bigat due to the weight of the silt above that point. Tama ba? Kaya ito ay compression pero positive yung sign na ginagamit natin. Yes, kasi halos lahat naman ng stress na kino-consider natin sa soil ay compression, kaya ipa-positive na lang natin. Ngayon kung may makita kayong negative sign, ibig sabihin merong tensile or tension. Merong tension doon sa soil. Kaya gumamit tayo ng opposite sign which is negative. And remember sa sinabi ko kanina about the capillary rise, from your fluid mechanics, this is associated with the tensile forces doon sa surface ng water natin. Kaya within the capillary zone, nakaka-experience yung pore water pressure natin ng tension. So kung tension yan, dapat ang sign na ginagamit natin ay negative. So para dito sa point sa taas at point A, ang reference lagi ng height ng tubig, laging ang reference natin ay yung ground water table dahil ito yung source ng capillary rise. So ibig sabihin, para makuha mo yung pore water pressure at this point, dapat yan ay negative. Sama mo na agad yung negative. And then same formula, gamma ng unit weight of water times Z. Ang Z nga natin, ang reference niyan ay groundwater table. So that is negative 9.81. Isama mo na yung 9.81. At yung point A natin ay 4 meters away from the groundwater table. Kaya nakamultiply ito sa 4. And the value is negative 39.24. Nasa left side siya ng ating diagram. Next, proceed tayo sa point B. So, negative ulit yan kasi nasa loob yan ng capillary zone. So, lahat ng pore water pressure natin within the capillary zone ay negative. Kaya ito ay negative 9.81 at ang distance niyan from the groundwater table ay 2 meters. Point B up to point C ay 2 meters kaya nakamultiply ito by 2. And para naman sa point C natin, dahil yung point C natin ay mismong groundwater table, syempre ang ine-expect naman nating stress dyan ay 0. Because groundwater, unit weight of water times the distance with respect to the groundwater table is the pore water pressure. Tama ba? Kung ang point natin ay mismong nasa groundwater table, edi 0 yung distance na yon. Kaya 0 lagi ang pore water pressure at the ground water table. So, next, punta tayo sa point D. Sa point D, dahil ito ay nasa ilalim na or wala na siya sa capillary zone, dahil submerged na yan, positive na yung value niyan. So, ibig sabihin, below the groundwater table, positive pore water pressure, above the groundwater table, doon sa part ng capillary zone, negative pore water pressure ang makukuha natin. So dito sa point B, that is 9.81 pa rin para sa unit weight of water times the distance of that point, point D, papunta sa groundwater table, that is 1. Ito. Kaya naka-multiply siya sa 1, giving us 9.81. And for point E, so ganun din, kunin mo yung product ng 9.81, the unit weight of water, tapos yung 2, yan yung distance from that point, papunta sa groundwater table, that is positive 2 na tayo, positive na yan kasi wala na tayo sa capillary zone, and that is, the value is 19.62, at itong line na to ay same slope, dahil pare-parehas namang water yan, wala namang nagbagong property dito sa system natin regarding sa water. So now that we have completed the total and neutral stress, pwede mo nang kunin yung effective stress by taking the difference between the two stresses. So para sa ating effective stress, 0 minus negative 39.24. So negative sa negative, magiging positive ito, kaya ang magiging stress natin, effective stress natin at point A is 39.24. So, kanina sa problem number 1, 0 tayo dito 0 tayo sa ground surface, ano. So, ngayon dahil nagkaroon ng capillary rise, nag-increase yung effective stress from 0 naging 39.24. So, yun yung effect ng capillary rise. Pinatataas niya yung effective stress ng lupa para sa region ng capillary zone. So, okay na yan. So, meron na tayo para sa point A. Proceed tayo sa point B. Kunin mo ulit yung difference. 39.24 minus negative 19.62. Magiging summation na to. Kaya, magkakaroon tayo ng value of 58.86 para sa point B. Effective stress na yan. Kasi hinahanap din yan sa problem. The effective stress at points A, B, C, D, and E. And then, sa point C, difference lang nitong dalawa, 78.48 minus 0 is 78.48. And sa next D, sa point D natin, 98.10 minus 9.81 will give us 88.29. Hanggang dun sa ilalim, kunin mo lang yung difference niyan. Ayun na yung ibibigay sa yung effective stress for that particular point. So, ito yung pressure diagram ng soil profile na to, at malalaman mo na rin yung effective stresses at points A, B, C, D, and E. So, the effect of capillary rise is increase in effective stress. Yun yung epekto ng capillary rise. Napakahalaga ng computation ng effective stress dahil unang-una, ito yung ginagamit para ma-measure natin yung strength ng soil. Kaya nga kapag ang effective stress ng soil is 0, meron tayong tinatawag na quicksand or the boiling condition of the soil na kung saan ay hindi niya na kayang isupport pa yung any vertical load. So babagsak na lang ng babagsak kung ano man yung inilagay mo dun sa soil na yan na ang effective stress ay 0, hindi niya na isosupport yung vertical load na ipapasa mo sa kanya. So, napakahina ng loop ng soil at that condition. So, kaya, iwasan nating maging 0 yung effective stress. So, mas maganda kung mapataas yung effective stress dahil ibig sabihin nun, papataas mo yung strength ng lupa. So, regarding the strength, para sa effective stress, paano naman, ito kasi natural phenomenon itong capillary rise, talagang hindi mo naman pinupwersa yan na umangat yung tubig dahil natural na nangyayari yan sa ilalim ng lupa. So ngayon, yung next topic naman natin is, pwede natin siyang iset up kung saan pwede tayong mag-allow ng flow doon sa soil. Ano naman kaya ang magiging effect noon sa effective stress ng lupa? So, yung next topic natin ay effects of water flow in the soil stresses. So, water flow, so meron tayong upward flow or downward flow. Iba yung upward flow sa capillary rise kasi ang capillary rise nga ito ay normal na nangyayari Samantalang yung water flow na upward, pwede mo naman kasi siyang puwersahin, lagyan mo ng inlet na kung saan dadaan yung tubig pataas doon sa soil, so pwede mong i-set up yan. So, ano ba yung mga effects? Ano nga ba yung maging effect ng water flow? Malalaman natin yan dito sa topic natin. Kung patataasin ba niyan or pabababain yung effective stress. So, when the water flows through soils, it exerts forces called the seepage forces on the individual soil grains, and the seepage forces affect the intergranular or the effective stress in the soil mass. So, ano yung seepage force? So, seepage force can be calculated using the formula I, which is the hydraulic gradient. Familiar naman tayo sa hydraulic gradient, that is delta H, or the change in water level at two different points divided by the length of that, or the distance between the two different points, and multiply by the unit weight of water. So if you want to solve the critical seepage force, just use the critical hydraulic gradient times the unit weight of water. Saan ba natin makukuha yung critical hydraulic gradient? Sa formula ng effective unit weight. Kasi sa effective unit weight, nakalagay itong GS minus 1 over 1 plus E. So, pwede mong gamitin yon to calculate the critical hydraulic gradient. So, ito yung formula na gagamitin natin para sa seepage force. Okay, so, ayan. Ito yung una nating gagawin. So, since kailangan nating makompare yung effect ng upward flow, downward flow, kailangan muna natin syempre i-analyze muna yung no flow. Syempre, paano mo mako-compare kung nag-increase ba or nag-decrease yung mga stresses due to the different types of flow. So, dito sa no flow, so sarado yung valve, so walang nangyayaring flow ng tubig. Pag naglagay tayo ng piezometer dito sa points A, C, and B, para lang ma-identify natin yung pore water pressure, pare-parehas siya ng level kapag no flow. So, ibig sabihin, yung pore water pressure at point A, that is the unit weight of water times this height. And then, sa point C naman, the pore water pressure at point C is the unit weight of water times this height. Medyo mas mataas kasi mas malalim na naman yung point C. At yung point B naman is sobrang taas din dahil siya yung pinaka-bottom ng ating system. Siya may pinakamataas na pore water pressure, that is the unit weight of water times this height. Pero pantay-pantay yan, kaya madali mong ma-identify or ma-measure yung mga height sa piezometer. So, ginagamit lang ang piezometer para ma-solve yung pore water pressure. Pero sa pag-solve ng total stress, ganun pa rin, gamma H times plus gamma H. So, walang magbabago. Sa pore water pressure lang naman nakaka-apekto tong effects ng water flow in the soil stresses. So, ganyan yung setup kapag no flow. What if nagkaroon ng flow? Let's say, binuksan yung valve, and then, nag-allow ng inflow. Ayan, merong tayong input ng tubig dito, making the water, ito binuksan natin, so ibig sabihin yung tubig is magpo-flow downward. So, lalabas yan dito sa ating tube. So, ano kayang mangyayari sa stress? Ito yung setup para sa downward flow. Sa point A, walang effect. Dahil ganun pa rin yung ating height ng water column sa piezometer natin. Pero kung papansinin mo yung point C and point B, bumaba na yung tubig. Anong dahilan kaya ng pagbaba ng tubig? So, ito ay head loss, tama ba? So, between point A to point C and point C to point B, nagkaroon tayo ng mga head losses. So, bakit ba nagkakaroon ng head losses? This is because of the friction. Kung ang tubig natin ay manggagaling dito, so, let's say mag-uumpisa yan sa point A, magpo-flow through the soil, nagkakaroon ng friction between the soil solids and the water particles bago ka makapunta sa C. Ibig sabihin, nagkaroon tayo ng energy dissipation because of the friction. So, nagkaroon ng energy loss, bumaba yung energy natin sa point C, kaya yung head loss natin dito, yung height of water natin dito, bumaba rin dahil sa head loss or the friction loss. Ganun din sa B. Dahil from point A, to point B, napakalaki or napakahaba na ng dinaanan ng fluid particle natin, kaya ina-expect natin na mas malaki yung loss, head loss para sa point B compare sa point C. Ayan, so mas malaki yung loss. Kaya mapapansin mo pababa yan, pero ang kinaganda nito, dahil consistent lang naman, para sabihin natin para dito, dahil consistent lang naman yung property nito, ito ay linear. So, pwede kang gumawa ng triangle dyan to calculate the certain heights. Okay lang yun dahil linear naman ang kalalabasan ng hydraulic gradient natin. So, ito, yung slope na to, yan yung gagamitin natin sa pag-solve ng hydraulic gradient. So, yan yung downward flow setup. Tandaan nyo lagi na ito ay pababa dahil nagkakaroon ng energy dissipation from point A to point B. Bumababa yung energy natin. What if the flow ay upward naman? So, nanggagaling sa ilalim yung flow pataas. Before pala tayo mag-proceed doon, check muna natin. Anong effect ng pagbaba ng pore water pressure doon sa effective stress? Ito yung formula natin. So, dahil bumaba yung height ng tubig dito, syempre, liliit yung pore water pressure kasi nakadepende yun sa height Tama ba? So, kung nabawasan to ng height, edi liliit na yung value ng pore water pressure natin. At kapag lumiit yung value ng pore water pressure, liliit yung ima-minus mo sa total stress. Therefore, magbibigay yan ng mas mataas na effective stress. So, yun yung kinaganda ng downward flow kasi pinapataas niya yung effective stress. Kung mapapansin mo rin sa setup, oo nga naman, talagang palalakasin niya yung soil dahil kung mag-a-apply ka dito ng tubig at yung flow ng tubig natin ay pababa, ang tendency ng seepage force natin is parang kinokompact niya yung lupa. Sinisiksik niya pa ilalim kaya mas tumataas yung strength ng lupa kapag downward flow. Kapag upward flow naman, so ito naman yung magiging setup. So ang upward flow, dito manggagaling sa ilalim yung flow kaya yung energy natin sa point B ay mas mataas compare sa energy at point C and point B. Tama? Dahil yung fluid natin dito, hindi pa naman siya nakakapag-flow through soil kaya wala pa masyadong head loss. Kaya mataas pa yung energy at point B pero as the particle moves upward to point C, nagkakaroon na ng friction between the fluid particle and the soil solids, bumababa na yung energy galing dito, bumaba na ng konti, tapos magpo-flow po ulit papuntang point A, mas lalong bababa rin yung tubig. Pero lagi nyo tatandaan na at point A, kapag naglagay ka ng piezometer, it will have the same height ng tubig dito. Ayan, hindi naman yan magbabago. So, ano naman nangyayari? Ano namang effect ng upward flow? So, kung mapapansin ninyo, dahil tumataas yung water column natin dito sa piezometer, ibig sabihin, tumataas yung value ng E. Kung lumalaki yung value ng yung U, ng ating pore water pressure, kung tumataas ng tumataas, at ima-minus mo doon sa ating total stress, edi lumiliit yung value ng effective stress natin. At ayaw nating mangyari yon dahil baka dumating yung time na yung pore water pressure mo ay equal na rin sa total stress na kapag minus mo ay 0, ang effective stress mo ay 0, napakahina na ng lupa natin. Makikita mo rin yan sa figure na kung ang seepage force natin ay pataas, hindi niya kinokompact yung lupa. Ang ginagawa niya ay parang nagiging nabubuhaghag kasi tinutulak mo pataas yung lupa, kaya humihina yung lupa kasi naghihiwa-hiwala yung mga particles natin because of this seepage force. So, yun yung effect ng water flow sa soil stresses. Kapag downward, patataasin niya yung effective stress. Kapag upward flow naman, pahihinain niya yung soil natin dahil pinabababa niya yung effective stress. So, I hope na naintindihan yung effect ng water flow sa soil stresses. Dahil magsasolve tayo ng problems para makita nyo numerically na may computation talaga na totoo na bumababa, tumataas ang effective stress depende sa types of flow. Problem number 3. The figure shows a layer of granular soil in the tank and the rate of water supply is kept constant. Evaluate and analyze the stresses for the following conditions. So, yung tatlo, we have no flow, upward seepage if the head loss is 2.5 and downward seepage if the head loss is 2.5. So mamaya na muna yung upward and downward seepage. Focus muna tayo sa part A, which is no flow. Kasi doon natin i-compare yung value na makukuha natin sa upward and downward flow. So ito yung setup. So dahil walang flow, actually pwede mo na agad kuhanan yan ng total stress, pore water pressure, and effective stress. Tulad ng ginawa natin sa problems 1 and 2. So gawa mo na, i-extend mo lang ulit yung lines para dito sa points sa pinakataas, tapos point A, point C, and point B. Given na yung unit weight, saturated unit weight ng soil, so hindi mo na kailangan pang computin. Unless ang binigay ay ibang property, gamitin mo yung mga properties na yun to calculate the unit weight. Pero ngayon, mabait dahil ibinigay na yung value ng gamma. So, let's start with the computation of the total stress. At point A, syempre, 0 pa rin naman yan. 0 pa rin naman ang total stress natin. Right. And sa point B, ito kaya nyo na itong gawin, kaya nagdire-diretso na yung graph dahil ang gagawin mo na lang is gamma H. Gamma ng what? Yung point A, sa taas, ito yung stress. Tubig lang naman to, so 9.81 times 0.5. Stress pa rin yun na na-experience ng A, kaya part siya ng total stress. So that is 4.905 yun. Plus, yung 4.905, dadagdagan mo ng stress due to this layer from A to point C. So, ang layer at ang stress natin dito ay 20 times 1.9. Idadagdag mo lang siya sa 4.905. So, ito, kayo na yung try to solve it yourself dahil nagawa naman natin to sa problem 1 and 2. Check na lang natin kung parehas kayo nung nakuha dito sa illustration. So, para sa point B, i-total mo lang lahat ng stresses dito sa tubig, sa stress sa AC, plus mo yung stress sa CB, dapat ang ibibigay dyan ay 64.905. So, yung computation pa rin natin sa total stress, unit weight times the thickness. Alright? So, kaya tayo nag-come up sa ganitong formula. So, practicein nyo to. Next, we have the pore water pressure, and for sure, kayang-kaya na rin ang pore water pressure dahil ang computation natin dito is unit weight of water times the thickness kung saan ka kumukuha ng stress. So, dito, 0 pa rin tayo. So, dito sa point A, pag kinuha mo yung pore water pressure, that is the height of water, same pa rin, ano? So, 9.81 para sa unit weight of water times 0.5, ang ibibigay pa rin sa atin ay 4.905. Ganun din sa point C, 9.81 times, pwede mo nang itodo from point C hanggang doon sa tuktok. And para naman sa point B, pwede mo na rin itodo 9.81 times the height, that is 1.1 plus 1.9 plus 0.5. Total na yun. Total na yun. Hindi mo na i-add yung 23 kasi na-total mo na yung height, that is 34.35. So, check nyo rin. Try nyo rin i-solve and then compare nyo dito sa nakuha kong graph or ating diagram. So, ngayon na meron na tayong total and neutral stress, pwede na tayong mag-solve ng pore water pressure kasi kukunin lang naman natin yung difference between this graph and this graph. Kaya, ang ating effective stress ay ito. 0 minus 0, 0. Ito, sa point A, 4.905 minus 4.905, 0 pa rin naman yan. And then, same as with other points sa point C and sa point B. So, ito yung value natin. 19.361, 30.557 para sa point C and point B respectively. I-compare natin yan mamaya kapag kinonsider na natin yung may flow, downward or upward flow. So, babalikan natin yung mga effective stresses na yan. Kaya, mag-proceed na tayo sa part B ng problem number 3. Ayan, upward seepage. So, yung total stress, hindi naman magbabago yan. Hindi naman maapektuhan yan ng upward seepage. Dahil ang naapektuhan ng seepage ay yung pore water pressure, kaya kinopya ko na lang ulit. Ayan pa rin naman yung ginamit natin para hindi na tayo umulit. Ngayon, dahil upward seepage ito, lagyan muna natin to ng piezometer para ma-identify na makita natin kung hanggang saan yung tubig. So, pag naglagay ako ng piezometer sa point A, syempre ang level niyan, same lang din ang level dito sa tubig. Ayan. And then sa point C, ayan. Remember na sa setup natin ng ng upward seepage. So, manggagaling dito yung tubig sa ilalim, manggagaling sa point B, mag-start sa point P. Kaya, mas mataas ang energy ng point B compared to the other points doon sa soil. Kaya, dapat ang makikita nating water level sa ating piezometer pataas from point A to point B. Alright, so ayan, meron na tayo. Ngayon, ang gawin natin, lagyan natin to ng designation. Ayan. So, kung i-reference ko to para sa aking triangle na mamaya gagamit natin for ratio and proportion, so yung slope ng line na to is the hydraulic gradient. Okay, so ang gagawin natin is ilabas ko lang para medyo naka-zoom out naman. So, let's name, since hindi natin alam tong height ng tubig na to sa piezometer C, edi consider ko muna siya as Y1. And then, ito kaya, alam kaya natin tong height ng tubig sa piezometer B? No. Siyempre, yun yung una nating masasabi. Pero, alam natin yan. Kasi according sa problem, the total head loss ay 2.5. Bakit doon ko nilagay? Pag sinabi nating total head loss, ito yung total energy na nawala from the start hanggang dun sa dulo ng flow natin. Eh, di ba nag-start ang flow sa point B? So, ito yung total energy niyan. Tapos, habang nagpo-flow siya through soil hanggang point A, nababawasan yung energy natin hanggang sa mag-come up tayo dito. So, ang head loss from point A, which is the last part ng flow, hanggang sa doon sa beginning ng flow point B, ito yun, yung difference ng dalawa. So, ito yung point A, ito yung point B, yan yung total head loss, kaya nagbigay tayo dito ng 2.5. Lagi nyo tatandaan nyo na, sa end and sa beginning, doon lang natin nire-reference yung total head loss. So, ilagay naman natin yung para sa horizontal distance. So, itong point na to, galing yan sa piezometer A, at itong point na to sa Y1, galing yan sa piezometer C. At yung distance na to is actually the distance between point A to point C. So, tingnan natin yung point A and point C, at ang distance sa pagitan nila ay 1.9. Okay ha, tandaan nyo ha, na itong horizontal distance na to is actually the distance between points A and C. At dahil yan ay 1.9, pwede mo namang ilagay na lang na 1.9 to. And the distance from this point, that is point A, and up to this point, which is point B, tingnan natin dito, ang point A to point B ay 1.9 plus 1.1, that is 3 meters. Ayan na, kompleto na yung triangle mo. By ratio and proportion, pwede mo nang masolve yung unknown na y sub 1. So, by ratio and proportion, ito yung magiging solution natin. Y sub 1 is therefore 1.583 meters. So, yung 1.583 meters, measured yan dito. Ayan, dito lang. Hindi siya in total height, ha. Dito lang siya manggagaling kasi kinuha lang natin siya sa triangle. Kaya, isa-isahin na natin. So, at point A, dahil meron na tayong mga heights, at point A, yung height ng piezometer natin, yung height ng water level sa piezometer A, ito yun. 0.5 lang naman yung height na to, kaya 0.5 pa rin tayo dito. Sa point C, yung height ng water from point C, manggagaling tayo dito, aangat tayo ng 1.9. Ito yun, 1.9. Tapos, from this point, aangat ulit tayo ng 0.5 para nandito na yung tubig. Kaso nga lang, meron pang increase which is 1.583. So, i-add lang natin 1.9 plus 0.5 plus 1.583, giving us a value of 3.983 para sa total height ng water sa point C. And last, at point B, galing tayo sa pinakailalim para makuha mo yung total height ng tubig dito sa piezometer, that is 1.1 plus 1.9 plus 0.5. Dito pa lang yun, idagdag mo pa yung 2.5 kasi mula dito hanggang dun sa tuktok, that is the total head loss, 2.5, i-add mo lang, will give us 6 meters. So, I hope na nakakasabay tayo doon. Now that we have the height of water in each piezometer, pwede na natin gawin ang computation ng pore water pressure. Siyempre, yun lang naman talaga yung goal natin dito sa upward seepage. Yung makompute yung mga bagong value ng pore water pressure. So, umpisa natin sa tuktok ulit. Ayan, so 0 pa rin naman yan. Hindi naman nagbago yan, 0 dyan. And then, sa point A, ang pore water pressure is height pa rin ng tubig. 9.81 times height ng tubig, 0.5. Ito pa rin yun, kaya ang ibibigay ay 4.905. Ngayon, dito tayo magbabago sa point C. Kasi sa point C, ito yung point C natin, 9.81 times the height of water at piezometer C. So, ito yung 9.81 natin, the unit weight of water. Ano nga ba yung height ng tubig sa piezometer C? Ito na-solve natin, 3.983. So, kunin mo lang yung product ng dalawa para sa pore water pressure at point C. And that is 39.073. And lastly, para sa point B, ganun din yung gagawin natin. Height, the unit weight of water times the height of water at point B. In piezometer, yan ay 6 meters, kaya 9.81 times 6, giving us a total value para sa pore water pressure at point B na 58.86. O yan na, kompleto na. Meron ka ng total and pore water pressure, kaya madali na yung susunod. Dahil sa effective stress, kunin mo lang yung difference nung dalawa. So, i-move lang natin. So, para makuha natin yung total effective stress, kunin mo lang yung difference. So, sa first level natin, 0 minus 0, 0 pa rin. Ito, 4.905 minus 4.9050, same as with the other points. Kunin mo lang yung difference nung total and neutral stress. Ito yung magiging graph. So, I hope na parehas tayo nang nakuha, na na-compute. Na compare natin yan sa kaninang nakuha nating value sa no flow. Ito, ilalagay ko lang dito. Ito yung stress sa no flow. So, kung i-try nyo i-compare, 19.61 siya dati sa point C nung no flow. Kasi nung nagkaroon ng upward flow, bumaba. Naging 3.832. So, napakalaki ng change, ng decrease kapag nagkaroon ng upward flow. Humina talaga yung lupa natin dito. Ganon din sa ilalim. Sa point B, na dati, nung walang flow, mataas ang effective stress, kaso nung nagkaroon na ng upward flow, bumaba na, naging 6.045. Napakalaki ng difference. Alright. So, yun yung effect. Nakita natin yung effect ng upward seepage doon sa effective stress ng lupa. Pero hindi pa tapos dahil meron pang isa para sa part C. Downward seepage naman, pero yung total head loss pa rin natin ay same pa rin as 2.5. So, ang flow natin manggagaling sa point A. So, mag-start ng point A, mag-flow through point C hanggang sa point B. At dahil manggagaling sa point A, si point A ngayon ang may pinakamataas na energy compare sa point C and point B. Pero dahil si point A nandyan sa unahan, kaya yung level ng tubig niyan, pantay lang dito. Which is 0.5. So, meron ka ng height agad ng piezometer sa point A. Sa point C, so, in-expect natin na mas mababa. Kasi nagkaroon na ng friction yung flow natin, kaya nadidissipate na yung energy from point A to point B. Kaya ito na lang, bumaba na siya. Pero hindi pa natin alam kung ilan yung height niyan. Mamaya, i-compute natin yan using the same principle of proportioning. So, lagay na rin tayo ng piezometer sa point B. Ayan, mas mababa na rin yung energy natin. So, from here, pwede tayong maglagay ulit ng triangle para malaman yung mga corresponding heights of water sa piezometer. So, ito, ilabas ko lang. So, i-y1 ko pa rin yung unknown height. Ito yon. Tapos, yung total head loss kasi now natin ay 2.5 pa rin. So, ibig sabihin, kung dito nang galing yung flow, so, siya may pinakamataas na energy at dito natapos yung flow, siya may pinakamababang energy at ang difference ng energy nila is the total head loss from point A to point P, that is 2.5. At ang distance pa rin mula dito hanggang dito, that is point A and point C. Kunin mo lang yung distance between point A and point C, 1.9 pa rin. And point A and point P, that is 3 meters naman mula sa, ayan, mula dito hanggang dito sa kabilang side. That is from point A to point B. So, by ratio and proportion, so alam niyo na yan kung paano ginagawa ang ratio and proportion to calculate y sub 1. Ganun pa rin naman yung value ng y sub 1. Wala namang nagbago kasi dun sa mga values na inilagay natin sa triangle. Nag-flip lang yung triangle natin, pero same lang. So, ngayon, tingnan natin kung paano natin makukuha yung mga height ng tubig. So, para sa A, ganun pa rin, 0.5 pa rin naman yan. Ito. Pero sa point C, hindi Hindi natin idadagdag to. Kasi kung mapapansin mo sa point C, para makuha mo yung height, manggagaling ka dito, mag-a-add ka ng 0.9, ito yon, plus, hindi natin to alam yung maliit na yan, pero para mas madali, mula dito, umakyat muna tayo hanggang dito. That is 1.9 plus 0.5. Nandito na tayo. That is 1.9 plus 0.5. Bago natin i-minus yung y sub 1. Ayan, so ang y sub 1 natin dito, kanina kasi naka-add yan. So ngayon, i-minus natin dahil nabawasan na yung energy, 1.583. Giving us a total height of 0.817. Medyo OA lang yung aking exaggerated lang yung figure ko. Dapat kung 0.817 to, dapat medyo nasa baba pa to, no? Pero okay lang yan, assumption lang naman yung illustration natin. Para naman sa point B, o yan, punta muna tayo mula dito sa point B hanggang itodo na natin hanggang dito sa taas. That is 1.1 plus 1.9 plus 0.5. Ayan yun. Bago natin i-minus yung total head loss, which is 2.5. Kaya ang ibibigay sa atin na total height ng water at point B is 1 meter. Although, parang hindi naman totoo. Pero yan yung computation natin. Nasa illustration lang yan. So, ngayon na meron tayong mga height of water in each piezometer, pwede mo nang kunin yung corresponding pore water pressure. So, para sa pore water pressure at point dito sa taas, so 0 pa rin yan. Tapos, dito, ganun pa rin. Pore water pressure is 9.81. The height of water is 0.5. Kaya, ganun pa rin yung ibibigay na value para sa point A. Pero pagdating sa ating point C, kung mapapansin nyo, magbabago na. Unit weight of water times the height of water in that piezometer, dahil nagbago na, naging 0.817, bumaba na yung pore water pressure natin at ito ay equivalent sa 8.015. And then lastly, para naman dito sa last point, sa point B natin, that is 9.81 times the height of the water in the piezometer, 1 meter. So ayan, ayusin na natin dahil nakuha na natin yung total stress and pore water pressure. Kunin mo na agad yung difference ng dalawa para sa ating effective stress. Ayan, difference lang yan. Kunin mo lang yung difference ng mga points na yan. Check nyo kung parehas tayo ng nakuha. Ngayon, kung i-compare ko yan sa no-flow, kanina, ito yung nakuha nating no-flow value. We have 19.36 and 30.57. Na kung i-compare natin dito sa downward flow, talaga nga naman na nag-increase yung effective stress natin from 19 to 34, from 30 to 55. Malaki din naman yung idinagdag doon sa ating effective stress. Kasi nga, kapag downward flow, parang kinocompress mo yung soil, giving it more strength. Kaya ang ating effective stress ay mas mataas compare sa upward flow or sa no flow. So that's it para sa video na to. So wait nyo na lang yung next topic natin. Ang next topic natin ay evaluation of the soil element using the Moore's circle.